12 by talking about the idea of Hooke's law. That was 12.1, Hooke's law. And Hooke's law was one of the quiz questions we had yesterday. And the idea behind Hooke's law is that as you apply more force, the spring, what does it do? Expands. Very good. As you apply more force, the spring either expands or, the opposite of expanding?
Contracts.
Yeah, contracts or squeezes or whatever you want to use as a term, right? Contracts would be the right word. So it stretches or it compresses. It expands or it contracts. But the idea is that Hooke's law tells us that there's some proportionality. Okay, there's proportionality. And I actually teach this topic to my freshman math students because it explains direct proportionality. It explains that as one thing increases, the other increases. But you guys know that already, that clearly F and X are directly related. You apply more force, you get more stretch, okay, or more change in length. Either it's stretch or compressed, one or the other. But it's a change in length is what X represents. So if you were to visualize this, you would be thinking of this. A spring at its rest, and then suddenly you apply force to that spring and it looks like this now. I'm going to call it F-app for applied. So you apply some force to the spring, and what happens to it? Clearly it stretches, in this case. Okay, it stretches. This is what you did in the lab. You hung a mass from the spring, and it went from the red spring, which is the free length, to what you see in green, which is the stretched length. Now, the actual distance stretched is this gap right here. That's what X is. Okay, from the dot at the end of the red spring to the dot at the end of the green spring. Okay, from here to here, linearly though, or vertically. The distance from this dot to right here. Now, if my applied force is down, which way does the spring pull? I'm prompting you, good, up. And obviously vice versa. If I were to somehow compress the spring upward, which way would it be pushing? Down. It's opposite because of Newton's laws, right? A reaction equal opposite reaction. So the spring force wants to restore the spring to its regular shape. Hence, the spring force is called a restoring force. A pendulum in motion, right? A pendulum that's moving back and forth, what restores it to its equilibrium? What force is that? Gravity. Okay, the weight of the object or the force of gravity. So, what we're going to recognize, and some of you did not recognize this, through the lab, through the notes, and then made the mistake on the quiz. K cannot be negative. K cannot be negative. And it's easy to recognize it as this. Watch. If I think of the applied force as being down, let's say I apply a force of 10 newtons down, and it gives me a stretch. Let's say the original spring was 6 centimeters, and the new length of the spring is now going to be 13 centimeters. The stretch would be obviously 7 centimeters. Well, here's the thing. If we think about the spring force pulls back upward. I think of up as positive usually. So I would probably plug in a 10 newtons here for the spring force. If that's the case, then it means that X, since the displacement was downward, needs to be considered as negative. Now, if you want to always consider displacement or the spring change as positive, that's fine. Then you have to consider the spring force to be negative. But either way, X or Fs needs to be negative. It doesn't actually matter which is. It's up to you to decide depending on the direction of motion and the direction of the orientation of the setup. If I had a horizontal spring instead of a vertical spring, well, then you got to consider left to right instead of up or down. So it's up to you to decide, but it really doesn't matter. Either Fs or X is negative, one or the other. All right? Now, my units of my answer for K would be what in this problem? Because so many of you just decided, you know what, I'm not going to include units. Or I'm going to include units that are newtons times meter, when it was in centimeters as it is, and it's not times either. What do you got? Newtons per meter. What is in this case, though? What would it be? Yeah, newtons per centimeter. So you take 10 divided by 7. You get 1 3/7, whatever that turns out to be. What does that turn out? That whatever, it doesn't really matter. 1 3/7 newtons per centimeter. That's what K would turn out to be. Because my original force was in newtons, my original length was in centimeters, it's newtons per centimeter. If you need it to be meters, and say it's a multiple choice, or for some reason you need to use this K value to find out the period, remember the period formula? Tau equals 2 pi radical m over K. That K needs to be in newtons per meter. So if this needs to be converted to newtons per meter, one of two things. Choice A, convert here. Convert right here. Becomes 0.07 meters, or negative 0.07 meters. Or convert here, but be careful when you convert here. To convert this answer we got, let me show you. Because a lot of you converted this but made a mistake. If you're converting centimeters and it's in the problem, you obviously just move the decimal 2 spots to the left. But if you're converting and it's in the denominator, you have to move the decimal to the right. Let me show you why. What does this come out to be as a decimal? Give me 1.4 what? Give me another decimal. Anyone have it? Just type it in your calculator. 10 divided by 7. What is it? 1.42? When you round it, it's 2.7, or what is it, 2?
That's 4.3 because it's 4.28.
4.28. All right, I'm going to leave the 8 for now, just for the sake of this example. And my units are newtons per centimeter, right? That's my answer we got. I left it as a fraction a moment ago. So if I want to convert this into newtons per meter, think of it like this. Remember how we did this with dimensional analysis? If I had 70 meters per second, write it as 70 meters in the numerator and 1 second in the denominator. Okay, think about it that way. So here, centimeter is in the denominator. I need that to be meter. So I put centimeter up top to get rid of it. Well, there's 100 centimeters in 1 meter. Cancel, cancel. So it turns out to convert this into newtons per meter, it's going to be 142.8 newtons per meter. Okay, a lot of people mixed up their numbers. They converted the other way. Make sense of your answer. It has to take more force to stretch something a full meter than it does to stretch it a centimeter. Right? To stretch this spring a centimeter, it takes you only a newton. 1.4 newtons, really. It takes 1.4 newtons of force to stretch it a simple centimeter. But if I want to pull on this spring until it stretches a full meter, I need to pull a lot harder, don't I? So this number can't go down. So use common sense. To convert from newtons per centimeter to newtons per meter, the number is always going to go up. Because it takes more newtons to stretch a full meter than it does take newtons to stretch a centimeter. All right, but this idea carries over. All right, so we're good with Hooke's law, the idea of Hooke's law. Let's talk now about simple harmonic motion and how it's related to this. This is section 12.2. 12.2, we talked about the motion of a spring, mass, and the motion of a pendulum, and how those two things are analogous to one another. Okay, they're analogous to one another. If you are really struggling with this, I'm gonna show a little bit right now, but if you're struggling still, what I recommend is this. If you just YouTube the phrase, motion of a mass spring system versus pendulum, you'll probably see a pretty cool animation that shows all the stuff I'm going to talk about. Okay, and I think I showed you a quick animation of it one day in class, of the spring and how as the spring is stretched, the force increases, and that equilibrium is zero force, etc., etc. But I'm going to show you that right now with the diagram. So think about a spring that's attached horizontally, God bless you. Okay, and let's say that at the end of the spring, some force is applied. And what happens is the force is applied to the right. So the spring, as a result, ends up like this. In the second state, it looks like this. Okay, that's the new state of the spring under some force that's being applied. That's what the spring looks like. Now, I guess I could erase this first line I put here to show that it's free. Okay, the first one is free. So you apply a force, the spring stretches. Now, when you let go of that spring, if there's no friction involved, what happens?
It will return past the free length and then kind of oscillate forever.
For how long? Forever. Okay, if there's no friction involved, you let go of this spring right now, it will contract to its regular length, then it will continue to compress the spring so it looks like, have you ever pulled down on a pinball machine, the spring compresses. Have you seen this? Try it sometime if you've never played pinball before. You pull down on the lever, the spring compresses. We let go, the spring shoots off. It's actually different. It's a different kind of spring. It's not extending when you pull. When you pull, it pulls on a lever which makes the spring compress. Okay, it's the same idea as these cabinets I showed you about. Okay, what happens here? There's a little spring right in here. You can feel free to look at it later. When I push on this, it compresses. When I let go, what does it want to do? It wants to go back to where it was. So what we have here, I've pulled on this spring to expand the spring, so it's going to want to contract. It's going to get back to its original shape, but it's going to go beyond the shape. And then it's going to compress. Then it's going to go back to the original shape, and then expand, and do this forever. It will oscillate back and forth in what we call, again, simple harmonic motion. Oscillations, another word, vibrations. It will oscillate indefinitely. It will continue to oscillate over and over and over, assuming no friction. Excuse me. But there is friction. So what happens actually?
They're gonna go back and then it goes a little bit.
Eventually coming to where?
Yeah, equilibrium.
Yes, back to equilibrium always. Equilibrium is stable. We want to be stable. The universe has a desire to be stable. Okay, so it always wants to go to a stable point. That's why a pendulum falls back to the bottom. It's stable at the bottom. Okay? Now, if we want to relate this idea to a pendulum, the idea of a pendulum is that you raise the pendulum up. It's the same thing as pulling the spring to extension. Letting go of the spring and letting it go back and forth is the same thing as letting go of the pendulum and letting it go back and forth. When the pendulum is at the bottom, the spring is at its free length. So again, this is analogous to this right here. Here's a pendulum at its normal location right here. We pull on the spring, it's the same thing as taking the pendulum and raising it up to right here. When I let go of the pendulum, it's going to start to oscillate. It's the same thing as this, oscillating back and forth. What do we call this angle theta? Or this stretch x? What's the term for that? There's a term for it we've been talking about. It has to do with waves. I'll give you a hint. It has to do with waves. Not frequency.
Altitude?
Not altitude. Amplitude. Careful. Amplitude. The amplitude, remember, was the height of the wave in that lab we did. And it was also the height of a transverse wave we kept looking at. The amplitude is the height. The height of the wave is literally how far you pull up on theta for a pendulum. The height of the wave is how far you stretch x. So if I were to graph the motion of a spring system, let me just demo before I take your question. If I were to graph the motion of a spring system, it gets stretched, goes back to equilibrium, compresses, goes back to equilibrium, stretched, back to equilibrium, compresses, back to equilibrium. Well, this is the stretch right here. That's x. That's how far it stretches. That's the amplitude. Well, what happens on the other end? Well, it compresses by a distance negative x, right? It's the opposite. If something is in harmonic motion, if you stretch it 2 centimeters, it'll go back to the equilibrium, and then it'll compress 2 centimeters. Then it'll go back to equilibrium and stretch 2 centimeters. And it will continue to do this over and over again, following this sinusoidal or periodic wave. Sinusoidal just means like a sine wave, okay? It's periodic though, because this will happen over and over. Really though, I'll draw in red. In red is what would really happen. Ready? Here's what would really happen in red. You'd get up to here, and it would be a little bit smaller, and be a little bit smaller, a little bit smaller, 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 smaller. And what would happen? It would stop.
That's with friction.
Okay, that is with friction, the line that's in red. Okay, in red is with friction. It's like when your car hits a speed bump, and then the car bounces for a second and settles out. Okay? Let's not be negative with this concept for today. No, I'm thinking you were going to say,
AC fluid?
what were you saying?
AC fluid?
Is that when your heart stops beating?
Yes.
Yeah, exactly. Okay, so we have 2 other things that are really related to this besides amplitude. The amplitude is the height of the graph. What was the length from one period to the next called? What was that called? There's two answers that are both acceptable. Wavelength is one. What was the other answer? Well, the crest is the top. So from crest to crest is a wavelength, yes. And trough to trough is also a wavelength, yep. And first starting point to when it reaches that axis after full cycle is these are all wavelengths, but there's another word for it also. Not frequency. Remember, frequency is the inverse of wavelength, the opposites. Frequency is how many waves occur in a given time, whereas wavelength is the actual length of the wave itself. So like if I were to make a lot more waves, like do this, ready with green here. This has a much higher frequency than the one I just drew before that. It's got a lower wavelength though. So those words are not the same, they're kind of opposites of each other. They behave indirectly. The period could also be considered the length of the wave. If this function was a function of time, if this axis is time here, the wavelength is also called the period. They're the same thing in that sense. But when we did this on a graph, we said, all right, you know what? This is called lambda, the wavelength, lambda. Okay, the frequency omega is inversely related to lambda. All right, if this is time, you could also have called this the period. The period length from here to here is also acceptable. You could have called this tau. Correct. Think about it, right? The longer the wavelength, the more time it takes for it to complete the cycle. If the wavelength itself shows that it's going to take a long time to go back and forth, that's the time it takes as well. Those things are really kind of the same thing. Okay? But here's the thing, ready? Both period and wavelength are inversely related to frequency. Both of them are. Now, we know this formula. I'll write it at the top, or I'll move up so you can see it. We know this formula tells us that period and frequency are inversely related for sure. Okay, period and frequency are inversely related. But the formula that shows us that wavelength and frequency are inversely related is this one. Which, believe it or not, these are the same formulas, close to at least. How do they look the same? Well, watch. Solve for lambda in the one on the right. If you were to solve for lambda, it would be lambda equals what? Lambda equals V over omega, right? Well, look. Tau, the period, over here. Let me point with the pointer so you can see later. Tau and the frequency are inversely related. They happen to be reciprocals of each other because this is a 1. Well, take a look at this. Wavelength over here and frequency are also inversely related, but they don't happen to be reciprocals of one another. Okay? The velocity is in the numerator. But do you see how that works? Isn't that interesting? Both the period and the wavelength are inversely related to the frequency. In different aspects, but they both are. Okay, now let's continue to talk. When a spring is fully stretched, we know that there's a force pulling back. When a spring is in equilibrium, there's no force on it. So if you were to look at your graph of an object in motion, right here, watch my hand. So let's say that this is equilibrium. Okay, let me make it a little more clear. Equilibrium is the middle of my body. This is stretched. This is compressed. Okay, make believe the wall is here. So when you stretch it, the force pulling back is at a max. It pulls back, it pulls back, it pulls back, it pulls back, it pulls back. It gets here. There's no force actually for an instant here. But it's got maximum velocity now. Very good. Out here, what's the velocity? 0, because it's at rest. I pull and I hold. I let go. 0 velocity, 1, 2, 3, 4, 5, max velocity. Now, this instant there's no force. Until what happens? It then starts to compress the spring. And the spring now pushes back until it compresses it all the way. And now the spring pushes back with a maximum force. No velocity, right? It stops. Starts to come back toward the middle again. And this continues to happen over and over again as we go through this process. This is related to our period formulas. So let's write them out. And please understand the physical significance of the formula, because that's where your multiple choice comes in. There are many of you that answer the multiple choice and don't always look at your formula sheet or don't always use the formula. Use the formula to help you. So if I were to tell you the following, okay? if I were to tell you the following, I double the mass. I double the mass that I'm hanging from this, this spring. Okay? I'm normally putting this small mass on, I put a bigger mass. What's going to happen to the period as a result? Just give me a general statement, not an exact answer. Very good. That's the exact answer. Nicely done. It's going to increase by a factor. In this case, if I double the mass, it'll increase by a factor of radical 2 because the 2 I'm putting in there is under the radical. Very good. And that makes sense because more mass means it's going to stretch further. If it stretches further, it's going to take longer to return to where it started. So it makes sense of the answer. If I increase K, what happens to the period? Which one? Increase or decrease?
Decrease.
Decrease. Come on, look at the formula. Remember what I just said. Where is K located? Where is K located? So, if you increase the K value, you decrease the period. Makes sense. Ready? Here we go. You have a spring that's very weak. You pull on it, the period will oscillate for a while. It's very weak, you can pull very easily. You got a spring that's very strong. You pull on it, let go, it returns very quick to where it was. Those are the 2 springs you used in the lab. The stronger spring came back to its shape much easier. Now, we didn't measure harmonic motion with the springs, we did it with the pendulum. Okay, but the same idea occurs. So with a pendulum, what affects the period? Only thing that affects the period in a pendulum is what? The length. The only thing that we can control, I should say. Because obviously gravity does, but we're on Earth. We'll say gravity is constant on Earth. So the mass of the pendulum does not affect the actual outcome. And we saw that in the lab. You tried a larger mass and a smaller mass, and you recognized that clearly they had the same period. Only the length of the cord affected the period. Okay, and that is directly related. The longer pendulum, makes sense of it. Release a pendulum that's really long. It does this. Ready? Huge arc sweeping out. Release a small pendulum that's only like this long. It's going to do this. Right? That's it. The longer the pendulum, the more arc length. It's like the radius increasing and having more circumference or arc length. It's the same thing.
It's like how you fix the clock.
No.
Yes, you're absolutely right. Because if you want the pendulum, the bobbed, absolutely. Was that one of the questions in your problem set? Nice, very good. And it is very much like how you fix a clock. Okay, the length of the pendulum changes, which increases or decreases the beat of the second, so it can stabilize your clock. Okay? All right. Yeah?
So you know how, like, it's kind of off, but, you know how when they, people who are getting ready to go on the road in, like, planes that do this, and then, like, when the plane's basically falling, it's no gravity?
Mm-hmm. I'm listening.
So, if you were at, like, not exactly, falling, but, like, kind of controlled falling, would that change the gravity like it does?
Yeah, so but what happened would be this. If you released the pendulum and you started falling, right, gravity would have no effect on this whatsoever. Because gravity would become zero in essence, the apparent gravity. Have you seen that music video? Did we talk about it in this class? Yeah. Have you seen the making of it actually?
Yeah.
Did you watch the making of it?
It took.
Yeah, if you haven't seen it, watch the making of it. I watched it the other day. I know you guys mentioned it, but I never saw the making of it. The making of that video is insane. They have to constantly, literally do this. Ready? Free fall. For like, 30 seconds every free fall it could take? That's it?
It was 27 seconds exactly, but I think they had to.
How many times did they do it?
It took them they had to do like 20 flights, and it took 45 tries.
It was incredible. But it's really cool to watch. You'll literally see them floating. And then what they did was they had a light that flashed when it was about to go back to gravity, and people would hold on to something. Because they'd be floating for a certain time.
Actually, when after the gravity, it would actually be double the normal gravity on Earth.
Because you're suddenly shooting back up. Yeah. So what happens is this. You're in free fall at the same rate as gravity, you're floating, and then suddenly it turns back around. A light would flash, and the people in the video would grab onto something so that suddenly they'd fall back down, they wouldn't hurt themselves, and then as they accelerate upward, they'd feel double gravity.
Wait, what video?
Okay, go.
Oh.
They made the Rube Goldberg machine.
And they have the one that's, like, with the treadmills?
Yeah, that was
Yes.
how they got.
12.2 was really all about periodic motion, right? Okay, that was the gist of 12.2, what we just went over right there. 12.3. 12.3 talked about what? Generally.
Waves.
Waves. Okay, waves. So let's talk about terms. Let's talk about terms first. Periodic. What is periodic? What is pulse? How do they differ? How do they kind of relate to one another?
Well, I know that the pulse is like what you send in a wave. I can only describe it. It can be longitudinal or it can be transverse.
Okay.
It's the force that you, not force you apply, but it's
How does it differ from periodic is the question.
it's periodic is it's sporadic. It happens on a period. It's like the cycle that it happens.
Okay, you're on the right track. Help her out.
Periodical is ongoing and pulse is just one at a time.
Yeah, that's all it is. Pulse is a single wave. Successively single waves creates a periodic wave. So if you have a source that is constantly generating a wave, like a radio tower, that is a periodic function. If you literally send one pulse down the slinky like we did, that would be a pulse wave. Now, we also talked about longitudinal versus transverse. Remember transverse, you think of the word transversal. There's your transversal. So transverse looks like this. Ready? The wave moves left to right, but the material of the wave oscillates up and down. That looks like a transverse, meaning there's a horizontal line cut by a vertical line. A longitudinal wave does this, and this is very difficult for me to draw. I'll show it in a minute. A longitudinal wave moves left to right, but take a look up. You're going to have to see this because I'm going to use the marker. Ready? It goes like this. It oscillates left to right as it moves left to right. Whereas a transverse wave oscillates up and down as it moves left to right. This is transverse at the top. This is longitudinal at the bottom. An example of a longitudinal wave was when I took the slinky and literally sent a pulse like that. So it was going like this as it moved forward. Whereas a transverse wave goes like this as it moves forward.
So on a test, we have like how would you draw onto the wave? You have the label, which is which.
You probably wouldn't have to because it's pretty impossible. As you can see, I couldn't even draw it here, right? Take that as a hint.
Longitudinal is parallel.
Correct.
Right?
And transverse, they're perpendicular. Okay, the oscillations are vertical, the motion is horizontal, so perpendicular for transverse. For longitudinal, if they're both horizontal, any two horizontal lines are always parallel. Examples of transverse waves, the easiest one is the EM wave that we're going to study we studied already in chapter 14 that we're going to talk about in a minute. The EM wave is two transverse waves oscillating back and forth, magnetic and electric. An example of a longitudinal wave, the easy one I gave you, was sound. Or remember I told you, think about like when you're standing in line at a concert. That's physically what it would happen. It would be a longitudinal wave. As like the first 30 people go in, the next 30 go to fill that spot, and it becomes like a little bit of a compression and expansion there. I don't know what you said.
I've never been to a concert.
You stand in line anywhere in life where there's a gap, you can see this.
Black Friday.
Sure, Black Friday works. She's just being sarcastic.
No, actually, I've never been to
Oh, I thought you would have. You like music.
Yeah, but I just
I mean, it doesn't like.
Where'd you go?
I went to.
I know, but usually people go to concerts by the time they're like going to college. Maybe, yeah, actually, that's true. My first like major concerts I went to, I was probably in
My
college.
first concert was Jonas Brothers before they split up.
I was Hillary Duff.
If it's one of those, yeah, maybe. Did you really?
But they didn't do anything like.
Nothing crazy.
It was the main thing they did. Like they had lighting effects and kind of illusions. The main thing was just tons of confetti. Like I don't know how they didn't run out. There was like mounds of confetti on the floor.
If there's one thing that OK Go has, it's spades. It's
Wait, so longitudinal is left to right, right?
It's parallel to the motion. Okay, if the motion is left to right, then the vibration is left to right. All right. We also talked or spoke in this section about these concepts of waves with amplitude, frequency, and wavelength. So let's quickly make sure we understand the formula that we just showed a minute ago. Okay, here's our formula right here. What we're going to see in this formula is that the velocity of a wave is equal to its frequency times wavelength. Now, if this is an EM wave, yes, if this is an electromagnetic wave, it always travels at the speed of light, which is given on your formula sheet. So if I tell you that it's an electromagnetic wave such as radio, microwave, gamma rays, infrared, ultraviolet, visible, all those, Okay, I will not. You do not have to memorize all those names, by the way. They will be on the test somewhere. I'll give you a hint. Okay, all the names of those waves will be on the test, but you should know applications of those waves. So like gamma radiation is used for blank. Okay, please don't tell me that microwaves are used for microwaves. Okay, and I put that if I ask for anything on the test that is not acceptable. Okay, so you should know applications of them that we spoke about. And hold on, I want to get to this. This value here is on your formula sheet on the bottom. As Ariel mentioned a moment ago, it is the variable c. Okay, it is the variable c that we're plugging in really for the speed. Remember, the velocity or speed of EM waves is the speed of light, which is 3 times 10 to the 8. Then, if you know either frequency or wavelength, you can determine the other one. So if I know frequency, I have a number here, I can solve for for lambda and get the wavelength. If I have the wavelength, I can find the frequency. For any EM wave, you can determine the other one of the two. If you have frequency, you get wavelength, and vice versa.
Change going from megahertz. That's where you multiply it by 10 to the 6.
That's correct. You should know mega for sure, because that's the one we used.
What if it's like, if it's say 29? I know the in-scientific notation has to be.
29 times 10 to the 6.
So would it be 10 to the 7 because it would
No.
be another place?
29 is not times 10 to the 1, is it? It's just 29. Or it's 29 times 10 to the 0, really. Isn't it?
Yeah.
10 to the 0 is 1. So 29 by itself becomes 29 times 10 to the 6.
So it's everything, and when you move.
It's whatever you had, just tack on a 10 to the 6 and get rid of the mega prefix. Yeah.
But if you don't know either of those values, you have to plug it into the formula first and like another formula first.
There is no other formula to plug into, so you have to be given one of the two. Okay? Yes? Got your question?
Yes, but.
Think about it. Or don't think about it.
Would the use for gamma rays on the test be considered reading the incredible?
If I asked for 2 and you gave it as 1, I'd probably laugh and give you credit, yes. Wise guy. You could just say cell mutation, i.e. the Incredible Hulk, because that's really what it does, okay? So 12.3, again, relates velocity, wavelength, and frequency. Now, this carries us over to 14.1, which is electromagnetic radiation waves, which is where the second formula, C equals omega lambda, comes from. This is given on your formula sheet, and so is this number right here. Okay, this is not given on your formula sheet. You have to realize that when it's EM waves, use the speed of light for velocity. Of theoretical knowledge in chapter 14. Chapter 14 was primarily theoretical, actually. What did you remember from chapter 14, section 1? What did you remember? Chapter 14, the first section, what was it about generally?
Light.
Light. Okay, it was all about light, the idea of light, the idea of EM spectrum. So we talked about the whole spectrum. We talked about how going from radio waves to gamma waves, the wavelength decreases. That makes sense, because the smaller waves, the gamma ones and the X-rays, those can penetrate our body because of the size of the wave. Do we somehow receive radio waves? No, they don't affect us. Radio waves do not. Radio waves on the order of like 2 to 3 meters in length. Okay? Radio wave is literally this long. God bless you. Okay, so the wavelength decreases as you go from top to bottom on that chart, and the frequency is the opposite. It would increase. Okay, it would increase. Yeah.
Memorize the chart and know that the gamma rays are bigger than the order.
You should understand that gamma rays are one of the smaller waves because of their application. You don't have to memorize it. No, absolutely not. If I remember that gamma rays and X-rays are used to study the body, those have to be small rays in order to study the body. Okay? So it really depends on that. What else in 14.1 did we look at besides this?
Not the flashlight, right? It's the.
I forget if the flashlight was in 14.1, but we did talk about that in general, yes.
That was 14.2.
I think that was 14.2, yeah? We talked about this. We talked about this, ready? I don't know if it was 14.1, but it's something we didn't get to yet, or we didn't speak about today. We talked about the fact that energy is proportional to the amplitude squared. We talked about this and we made an example. What was the example that made sense here? Anybody remember? How that if you have more energy, it creates a wave with a higher amplitude?
Oh, just like when kinetic and potential.
Not the sun. Louder. That's a good example, yeah. A little kid, we did discuss trampolines, but it wasn't this example. That works. A little kid on a trampoline, the oscillations, the amplitudes are very small. The kid has less potential energy. Now we get on the trampoline, we have more mass, we have more potential energy, which creates larger stretches of the trampoline, larger amplitude. Good example, Sam. What else? Anybody remember the one we did in class? It had to do with a pond.
Oh, if you throw a boulder.
Chris?
Pebble versus boulder.
Yeah, the pebble versus boulder. You want to explain it?
So you can throw a pebble in a pond, the ripples are smaller versus if you throw a boulder, the ripples can be.
I like your hand gesture.
And the ripples, good, right? They can't see it in the video though, unfortunately, but this is me doing this the whole time. But yeah, the amplitude increases as a result. Okay, very good. Now, while we're on the topic of direct or indirect variation with squares, let's also talk about brightness of light in this section, just for now. Because these things are very similar. Okay?
Mr. Howard, why are you stabbing that person? Mr. Howard, stop stabbing him. Why? Why?
So, like, what are you talking about? The brightness you see at the location is equal to the source's brightness, or the brightness at the other location, divided by the factor of increase squared. So let me give an example that makes more sense, okay? So let me give you an example of this. Can I move these up? Yeah. All right, so here's our flashlight. Let's draw a flashlight. I'm a pro at flashlights. All right? The light coming off. It looks like one of those bam, pow kind of like things.
Oh, yeah, that was comic.
Yeah. So ready? Here's the screen right here. Okay? And it's a sensor right there. And that sensor is located 5 centimeters from the source. And it reads a certain luminosity or a certain brightness level. And let's say the brightness level, I'm not even going to put units for now because I don't want to confuse you with units, but let's say it's 10. Okay? Anybody know what the units are for brightness? Yeah, usually lumens is what it is. Okay?
That's why I do it.
So now we take
Oh, that's so cool.
Now we take the distance and we increase it to 15 centimeters from the source. What's the factor of increase? 3. The factor of increase is 3. Focus. The factor of increase is 3. So the brightness at that location is 9 times less than what it is at the other location.
3 is deep.
Because it's 3
It's deep.
squared.
Yes, but like it's
Okay, because D is the factor of increase. Okay, so you would put a 3 in here and recognize that the actual brightness you see is the brightness at the other location. You can call it the source, but it's not really the source, so maybe I should just put like other. I don't know. The original location. Okay, the brightness you actually see is the brightness at the original location divided by 9 because it's an increase of a factor of 3 in this case. Now, quick, because we're running out. Math, you could expect mainly chapter 12. Definitely chapter 12. And if there's anything from chapter 14 mathematically, it would be using that V equals omega lambda formula because that was in 12.3 and it was also in 14.1. Okay? Yes. But 12.1, 12.2 are mainly going to be your math components. Okay? 12.1 and 12.2. Let's talk light and color and polarization. Okay? In this section, we talked about the visible light spectrum. We talked about the color you see being the color that's being reflected to you. Okay, it's being reflected. We talked about reflection in general. The angle of the incoming ray equals the reflected angle.
diffused or
Yes, we talked about a diffuse surface, which is rough and does not reflect well. We talked about a specular surface, such as a mirror, that is very smooth and very polished, that reflects very well. Okay, continue to look at 14.2, 14.4.